Greetings and salutations, magical chemists. I hope you are ready to dissolve all your troubles away by looking at the solubility equilibria. Well, we're going to start off by telling you how we might just have lied to you just a teensy bit. We've kind of pretended that compounds fall into one of two categories. They're either 100% soluble or they're completely insoluble. It's not actually true. In fact, most things that are quote-unquote insoluble can actually dissolve a little bit. And so we can use our knowledge of equilibrium to examine what's called the solubility product constant, or the equilibrium constant expression for solubility. It's represented as KSP. And so this is simply writing out your K expression for dissolving a salt or a solid. And of course, like all K values, this is going to be a constant when you're at a constant temperature. So let's take a look at KSP. So for a given salt, first we need to look at what the actual dissociation reaction is. Basically, how do you write what happens when it dissolves in water? Well, your reactant is a single thing. It's just the solid of your compound. And then we've got, of course, our equilibrium back and forth arrows. And we're going to show basically the particles that it will dissociate into. In this case, well, calcium fluoride will break apart into one calcium ion and two fluoride ions. So when you're writing your equilibrium constant expression, your KSP value, you may have wondered, I didn't give you very much space. Why in the world is that? Well, remember, pure solids are never included in your equilibrium constant expression. So in this case, there are absolutely no reactants being included in your K expression. So all you have are products. So for the KSP of our calcium fluoride, we're just going to take the concentration of our calcium ion, and we're going to multiply that times the concentration of our fluoride ion. But we are, of course, going to square the concentration of the fluoride ion because it dissociated to form two of them. Now, when you are writing a dissociation reaction, please remember that your polyatomic ions don't break apart. The polyatomic ions stay together. So, for example, when you're looking at potassium carbonate, it does not dissociate in water to form carbon and oxygen. Instead, it just breaks apart to form two potassium ions and a carbonate ion. So now that you have that, I would like you to take a moment to try this for yourself. So you're going to go ahead and write the KSP for the dissolution of potassium carbonate, and you're going to write the dissociation reaction and the KSP value for our last salt, aluminum sulfide. When you're ready to check the answers, unpause the video. So here's your KSP expression for your dissociation of potassium carbonate. Now let's look at the dissociation of aluminum sulfide. So this one breaks apart to form lots of ions, so it leads to a delightful KSP expression. In this case, we had to take the concentration of our aluminum ion and square it, and our sulfide ion and cube it. So much concentration. So I hope you definitely noticed the KSP expression will only ever have products when it is written. I added an extra exclamation point because it's so important. And the reason this happens is because when you're dissolving something, or dissolution, it always starts with a single solid reactant, and solids aren't included in an equilibrium constant expression. Okay, so now that we know that, let's go ahead and look at what the kind of a generic solubility constant expression would look like. Makes it look way more confusing, but it's really not. If you have a given salt with a cation of M, with N copies of it, and an anion of X, with M copies of that, well, of course, it's going to break apart to form NM cations and MX anions, each raised, of course, to their respective charges. And so that was what you would use to write your KSP expression. So just like any other equilibrium value, if you have a larger KSP value, you have more products. So that means more dissociation and a greater solubility. So the higher the KSP, the more of the substance will dissolve. And of course, smaller KSP, less stuff is dissolving, so you have lower solubility. Since we're talking about solubility, let's go ahead and remind ourselves of the basic solubility rules that you have to know. You only have to have memorized a very limited subset of solubility rules. Basically, you have to know three things that will always be soluble: alkali metal cations, ammonium, NH4+, and nitrate, NO3-. There are lots of other solubility rules in the world, but You only have to know those 3 things at the top. The rest will be provided for you if you need them. Okay, so that's the basics of solubility, but it turns out your KSP calculations are going to be just the same as any other equilibrium calculations. We're going to use a tasty rice table. So let's take a look at an example when we are dissolving silver sulfide into pure, delicious water. And then it tells you, well, the concentration of the sulfide ion is, this stuff, and they want you to calculate the KSP value. So let's start off with our rice table. Now to do that, you actually need to know what silver sulfide is, so you have to write the formula. Since we have an ionic compound, you have to consider charges. Remember that silver is a transition metal whose charge you must have memorized, and it has a charge of +1, whereas sulfide has a charge of 2- as an ion. So the silver sulfide salt, very alliterative, will be Ag2S. And then, of course, we are going to dissociate this. We're going to put it in water. So when you're setting up your rice table, it's important to recognize that we're starting with a solid, so you're not going to have anything on the reactant side. Solubility focuses almost entirely on the product side. Now, of course, before anything is dissolved, you have nothing on your product side because nothing dissolved yet. And then, when things start dissolving, well, you're going to produce twice as much, or 2x, of your silver cation as you will of your sulfur anion. So your equilibrium value here are simply going to be 2x and x. Well, remember, they gave you information in the problem. They said that at equilibrium, or when it dissolves in pure water, and this is what they mean, the concentration of your sulfide ion is 3.4 times 10 to the -17th. Not much, but it's there. Well, if that's the concentration of the sulfide ion, hey look, that must be the value for x. Well, since I know what x is equal to, it's really easy to solve for the concentration of Ag+, because it's just 2 times x. So now, when we want to go ahead and solve for KSP, well, we just need to write our KSP expression and plug in our known concentrations. So we're just going to go ahead, so our KSP expression, remember we had to square the concentration of our silver cation, and then multiply that times the concentration of our sulfide anion. And so that gets us a really tiny number. So that's our equilibrium constant for when we dissolve silver sulfide in water. Now, I do want to show you there is an alternate way of solving this, still using the rice table, same thing, but it basically skips a step, and you know me, I'm pretty lazy. So let's take a look at it. Well, in this method of solving, you still have to plug into the KSP expression. That's never going to change. But I'm going to skip the step here where I solve for 2x. And instead, I'm just going to write KSP in terms of x altogether, and only then go back and plug in for x. So here's what I mean. We know from our rice table that the equilibrium concentration of silver is going to be 2x. So I'll plug that in for my concentration of silver. And then the concentration of my sulfide ion is just x, so I plug that in. So now I can basically make this a little prettier in terms of x, and notice I have to square the 2 and square the x and multiply it all together, so I get 4x cubed. Well, now I can just, from here, take my value for x, which I had up above, and plug that in for x. And so it basically just cuts out a step in the math, even though mathematically it's still the same thing. So either way you want to solve it, it works. I will tend to do this value where I solve for everything with x first and then plug in, because it skips a step. And, just a teensy bit more efficient. And of course, the point is you get exactly the same value. All right, so let's go ahead and try one on your own. It'll be amazing fun. Okay, so you should go ahead and try this problem on your own, and when you get stuck or you're ready to check your answer, well, unpause the video. Well, hopefully you realize the first thing you have to do, figure out what the heck your formula is of your salt. Well, if I balance my charges, I have Ag3PO4 for silver phosphate, so now I can go ahead and write my dissolution expression. Sorry, my dissolution reaction. And now I can go ahead and plug in my rice table. As always, so when I initially put my solid in water, I am starting off with none of the ions at the beginning, so then I can just plug in for the change. So when you're writing for these and solving these KSP problems, you may notice these rice tables are pretty simplistic. So unless you actually are starting with an initial concentration of either, like what, your anion or your cation, which can happen, and we'll look at that later, but when they're both starting at 0, it kind of feels a little excessive to write all these steps out. So oftentimes what a lot of people will do, they'll actually just skip part of this. People will just be like, I don't need to write this because it's just going to be 3x and x. So people will make like a little tiny rice table and just show the change relative to x. So that's what I'm going to start doing in the future because, as you know, I'm lazy. But if you want to write the whole thing, more power to you, whatever works for you. Once we've reached this point, whichever way we use to get there, we recognize that they gave us information. They told us the concentration of phosphate when it's dissolved. So we know what our x value is. So now we can write our KSP expression in terms of x and then plug in and solve. Well, in this one, we've got a lot of x's going on because there was a lot of silver cations. So ultimately, we've got our 3 cubed, which would give us 27, times x cubed. So then we just go ahead and plug in, x to the 4th, yum math. And so now we can just go ahead and plug in for x. And then we found our KSP value, which is tiny, but not too tiny. That actually is not bad. They get way smaller than that. All right, so there's one more type of problem. We can basically go where instead of asking you to solve for KSP, we give you the KSP and ask you to solve for what are the ion concentrations at equilibrium. I hope you're seeing that these problems that we're doing with KSP are just like the problems that we did with any other K value, because KSP is still just working with K. So I strongly encourage you to go ahead and try this problem on your own. Make lots of squiggles. And by squiggles, I mean chemistry. And when you're ready to check your answer, unpause the video. So first we write out the dissolution of our lead 2 chloride. And then I'm going to do my little mini rice table where I just look at the change in x. Well, there's only 1 lead being produced, so that'll just be x. And there are 2 chlorides being produced, so that'll be 2x. So now I can go ahead and write my KSP expression in terms of x. I do want to strongly encourage you, before you plug in for x, actually write KSP with the concentrations. It doesn't take long and it really minimizes errors. And so that's how we can discover in terms of x, our KSP is equal to 4x cubed. And then remember, they actually told us the KSP value in this problem. 1.17 times 10 to the negative 5th. Hey, not too bad. That's actually pretty soluble. So now what we're going to do is go ahead and solve for our value of x, and then we can use that to plug in and solve for the concentration of our ions. So in this case, to solve for x, we have to take the cube root of 4.6 times 10 to the negative 6th. Wait a second. Oops. I was trying to solve that problem with the wrong KSP value. That was not going to go well. As I was saying, we're taking the cube root of 1.17 times 10 to the negative 5th divided by 4. Now, I wanted to remind you about something mathematically, because I don't know about you, but I never remember how to take the cube root of something in my calculator. But I do know how to basically raise something to a fractional exponent. And mathematically speaking, taking something to the cube root is the same as raising the entire thing to the 1/3 power. And that's something that's really easy to do in your calculator, especially because we're going to be taking lots of other roots, like roots to the 5th and roots to the basically large things that are awkward to find. But if you remember, when you're doing this, you just raise it to the fractional exponent, and these are really easy to plug into your calculator. And that's how you discover that x is a relatively tiny value. So now that we know that, we can go ahead and solve for the concentration of chloride ions, which is what the problem actually asked for. Well, since 2 ions of chloride are produced, we just have to multiply our concentration of x times 2. And we have the concentration of chloride. All right, before we are done, we have one last thing to talk about because there's a little bit of terminology that's different when you're talking about KSP. So let's look at that. So you may have noticed that the x term, when things are dissolving, well, that's always going to be equal to the amount of solid that dissolves, because the stoichiometric coefficient of the salt is always 1 in the dissociation reaction. Because of that, the x term actually has a special name. It's called the solubility, or molar solubility. Now, it is x in your KSP rice table. Some people will make a really special KSP rice table and use S for solubility instead of x. But mathematically, it's the same exact thing, and I really hate trying to confuse things by throwing another random letter in there. But you are totally welcome to use an S instead of an X. It means the exact same thing. And it is defined to be the amount of a solid that will dissolve in 1 liter of solution. And of course has units of molarity, capital M. Now, solubility is an equilibrium position, and therefore it can change. It can undergo shift left or shift right, just like any other equilibrium. If you have a larger molar solubility, basically larger value for X, that suggests that you're having more dissociation into ions, so that's a greater solubility, just like having a greater value of KSP. And of course, a smaller X value, a smaller solubility, implies you have lower solubility. Kind of goes with the name. So when you see KSP questions, their calculations are going to be exactly like what we just did on the previous page, but the language might be a little different. So let's go ahead and take a look at how these might be phrased. So they could tell you the molar solubility of barium fluoride is 2.45 times 10 to the negative fifth. Oh, and that should be in units of molarity. My bad. So use that to calculate KSP. Well, it sounds all fancy and stuff, but really just remember, they're just giving you your value of X. So they're actually making this problem super simple. So you should totally try this. It'll be amazing. And when you're ready to check the answer, go ahead and unpause the video. Don't forget to try it first. So we start off by setting up our mini rice table, and then we plug into our KSP expression. And of course, like the magical chemist that you are, I'm sure you wrote out your equilibrium constant expression before you plugged your X values in. So we get that our KSP is equal to 4 times the molar solubility cubed. So we just plug in the value for X. And there you go. Short and sweet. All right, let's try one more. So now we're looking at the molar solubility of nickel 2 carbonate, and they're giving you, it says calculate the molar solubility of nickel 2 carbonate, which has a given KSP value. Well, that just means solve for X. So again, something short and sweet. So you should totally try it, make lots of squiggles filled with chemistry, and when you're ready to check your answer, unpause the tasty, tasty video. So just like always, we make our tiny rice table, and then we write our KSP expression. Rewrite KSP in terms of X, and plug in for X. Oops, did I say plug in for X? We don't know what X is. That's what we're trying to find. We do know our KSP value, though, so we know that X squared is going to be equal to 1.4 times 10 to the negative 7th. So we just need to take the square root to solve for X. And remember that when you solve for X, which is your molar solubility, it does have to be in units of molarity. And then you're good to go. And you are now masters of solubility. So we will spend lots of time playing with all these delicious dissolving things in class. See you there.